Go?
Yeah.
Okay. So welcome everyone to November ABCD presentation. Today we are pleased to have with us Sam Birnbaum. He's the project lead for Digital Globe's GeoHive crowdsourcing platform. He joined Digital Globe in 2013 as an intelligence analyst for the Human Geography Information Surveys program. He has a bachelor's degree in international and comparative studies from the University of Michigan. And we also have Todd Backestow. He's the director of product management at Digital Globe, where he works to incubate, launch, and grow products that help answer key geospatial questions for decision makers. Todd joined Digital Globe through the acquisition of GeoEye, and before that worked in venture capital and investment banking. Todd holds a BS in information sciences and technology from the Schreyer Honors College at Penn State. So with that, I'll turn it over to Sam.
Thank you. So we're actually going to do this presentation in a few stages. Todd's going to start and give sort of a general overview of some of the types of things that Digital Globe likes to do, sort of the general theme of some of our products, and then I'm going to launch into a discussion specifically about crowdsourcing, as well as obviously the GeoHive system, and then we're going to go back to Todd to talk about some of the outputs that we release. So.
Great, thank you, Sam. Thanks for coming out to hear our talk today. We really appreciate it. We're really thrilled to be here. This is a great opportunity, and we're really excited to share a little bit about what we do at Digital Globe.
That's
So again, my name is Todd Backestow. I'm the director of product management. I'm primarily focusing on our U.S. government business, but I have a chance to work with customers across the board. And today what we wanted to do is just to start out and talk a little bit about what we do overall. And Sam and I, we had a lengthy discussion back and forth in a good kind of creative, thoughtful way around, well, how can we simplify that in a way that is meaningful, but also doesn't get too far in the weeds to start out. And so we're happy to go into details. But we thought that really when we boil down a lot of what we do, it really boils down to capturing data and information, extracting additional information and data, and then analyzing it to help produce answers for decision makers to answer key questions. And so we'll talk a little bit today about how we go about doing that and about some of the things that Digital Globe does that makes that unique. So let me put this into a little bit more specific context. When we capture information, we generally can capture it. There's a number of ways, but the two ways that we're going to talk about today are with commercial imaging satellites that we own and operate. I'll talk about our constellation and some of the unique characteristics of that constellation. We can also capture open source information as well. So information that's freely available on the internet, whether it's map data or other information that has location characteristics. That we can then enrich and put in further into a geospatial context. So once we've identified those areas, looking at open sources, we can point our satellites in those directions with high resolution, which I'll talk a little bit about, and high degree of accuracy, positional accuracy, as well as then how we can use capabilities such as crowdsourcing to create more information where those layers might not otherwise exist. And Sam's going to talk about that in detail. So first, let's talk about capture. So many of you probably know Digital Globe from our satellite imagery, and we're really proud of that. We're an industry leader in this space, and we continue to strive to be a leader with Earth imagery and various Earth imaging sensor technologies. So the graphic that you see in the upper corner there is showing what our collection footprint is. I believe it's pretty small to see, but I believe that's about 6 months of collection. So we actually have within our My Digital Globe tool, one of the options is you can select different periods of time and see what the image footprints look like. And one of the things I'll talk about is that this is a really useful tool when we think about mapping in a traditional sense for web mapping and whether it's online mapping tools and so forth. Many of those tools solve a problem of show me there. So you can see that an image has been collected there. You want to zoom into that place and look at it, right, and see those areas. Or you know a place, maybe it's your hometown, or maybe it's where you live or you work, and you can zoom in and see that place. So this again shows you the breadth of coverage. So on a daily basis, we're collecting over 3 million square kilometers of imagery a day, over 1 billion square kilometers of imagery over a year. Now there's varying degree of how much cloud cover and things like that, how much of what the yield is for useful information or useful imagery. But I think it's fair to say that there's a high degree of information that becomes available from this our constellation of sensors. Yep, we have a question.
A question about the patchiness about 30-day collection. I'm so used to see swaths of satellite collection coverage.
These are swaths. It just zoomed out to a level that it appears to be more of a point.
Oh.
But these are collection swaths.
Okay.
And this is across our entire constellation. I believe it's about, actually, I think that's closer to.
No, this one's 30
Oh,
days.
that's 30
6 months.
days,
Yeah,
okay.
this is 30 days.
In 6 months, we roughly are covering more of the entire surface of the Earth, the land mass of the Earth.
One thing I want to add here is that on any given day, we can take a picture of any place on Earth at least once, any day.
Because you can turn the angle.
Not only that, but just given the quantity of satellites we have in the air, which is Todd is about to talk about that.
How long do you keep the data? You keep everything for as long as you possibly can?
We store it in our archive, and our archive goes back to 1999. So really, the first imagery you'll see in the archive goes back to Iconos. Iconos it reached the end of its life after serving well beyond the expected life, and it was a great satellite. It was actually the first commercial sensor that was sub 1 meter resolution. And so in addition to the amount of imagery that we're collecting, we're also collecting spectral diversity. So particularly when you look at a sensor like WorldView 3, there's multiple bands of spectrum that we're collecting. So we have the 8 bands. We also have bands for SWIR, shortwave infrared. We also have additional bands for clouds, aerosols, water, ice, vapor, and snow, what we call CABIS. And this helps us basically collect these additional bands at the point of collection so that we can detect these sort of characteristics in the image. And Sam already talked to the revisit rates. And so you can see an example there of the imagery both is aesthetically beautiful when you're looking at it from a zoomed out perspective, as well as then when you want to zoom in to see some of the details. So you can, with a WorldView 3 31 centimeter image, you can begin to see what a person on the ground could look like, or a car, and distinguish between the difference of, for example, is something you couldn't necessarily distinguish the make and model of a car, but you could say whether it was a sedan or whether it was maybe a larger truck. This dives into the distinction of the resolution a little bit. So we go from a 1 meter to 70 centimeter, 50 centimeters, and then now 30 centimeters with WorldView 3. You can begin to read some of the markings. I know it's a bit hard to see on this screen, but you can begin to read some of the markings on the aircraft, on the runway, noticing some of the seam lines on the runway. So the amount of detail is significantly higher at 30 centimeters. Therefore, we can extract more information as well. We touched on our constellation, and so there to answer the question about the archive. We also then, so the reason that Iconos and QuickBird, even though those satellites are no longer in orbit, we include them on this chart because our archive does go back to include those imagery from those sensors as well. And I think the important theme with the satellite constellation is that all of these sensors are best in class when they were launched, and still even well after their launch, still continue to perform best in class as well. WorldView 3 I had the privilege of seeing launched last summer, and it's the highest resolution commercial sensor that's on orbit, and as we said before, collecting at 30 centimeters with an inaccuracy of generally less than 3 meters. So if you were to use that for navigate that imagery for navigational purposes, or if you're using that imagery for scientific work and measurements and so forth, the positional accuracy without ground control points, I might add, is significantly high on the sensor. And then we'll launch Worldview 4 next fall.
What are the specs on Worldview 4?
They will be comparable to Worldview 3. And so in terms of
30 centimeter.
the resolution, actually, it won't have all the same bands, but it's in terms of the resolution and so forth, it'll be comparable.
Right, and also 30, correct me if I'm wrong, Tom, but 30 centimeter is actually the highest resolution that we're allowed to sell commercially.
I believe there actually, so there was an effort to have the resolution restrictions lowered through our license with the U.S. government, and actually I believe it's even slightly lower, but that's what the resolution of the sensor is.
Is that mandated by, obviously, it's the federal government?
By NOAA, actually, it's with our license.
All right, so what about in other countries?
I'm not an expert on the policy, but my understanding is that other countries. So if we're imaging other places, it's has to do with our license, but other countries aren't necessarily. I mean, this is a U.S. government law. It's not something that other countries necessarily have to follow, to the best of my knowledge.
My question being more, if you launch a sensor that had higher accuracy,
Higher resolution or
higher
higher?
resolution, sorry, you could in theory come it down for the U.S. locations and have higher resolution in other parts of the world.
So the resolution limits are really imposed. It's through the license of the government, but you could theoretically, I don't think it also limits where you sell it either. So I don't want to speak into get into the policy parts of it, because as I said, I'm not where we focus more on the analytics of it, but that's my understanding of. And I think actually a good example of that is aerial imagery. To the best of my knowledge, there are no limitations on the resolution of aerial. So if you can fly an airplane there, or a drone, or another type of sensor, then these limitations wouldn't be something that would be of consideration. It's primarily due to a space-based sensor. So in addition to Earth imaging satellites, as I mentioned, we also are able to utilize data that's freely available in open source. And so this is actually an example of data that we some of which we're able to utilize from open sources. But this is our human geography data sets. Essentially, we're able to pull together data sets, as well as then from some imageries, some of this information that's extracted from our imagery, others enriched or licensed from other sources. And this is another example, though, so in addition to raster-based collection, there's also the ability to pull in other geographic information, which is could be text-based or could be vector-based as well, so points, lines, and polygons. And we'll talk a little bit about how we do that at scale. So I'm going to hand, I guess we'll start on this section and then hand things over to Sam here in a minute. So as I talked about, we have a long history within the commercial satellite imagery business of collecting images from space. So now the question then becomes, when you have this massive archive and when you're collecting 3 million square kilometers a day, which is about 70 petabytes of data, there's a lot of information in that goes beyond what an analyst can see in the picture. Where we're currently focused is around an initiative that we're calling a Geospatial Big Data initiative. And what we're really trying to do is unlock all the information, extract that from the images. And so you can see that can be from a variety of open source content. There's some imagery that's is publicly available. There's also our own imagery. And we're putting that together in a cloud-based platform where we're able to allow developers to run their own algorithms. They can run Digital Globe proprietary algorithms, such as our car counting algorithm, or they can run third-party algorithms, such as NV Analytics. It's one of the third-party algorithms that we have within our Geospatial Big Data platform. And so let me explain some of the examples of this, of what the benefits of our Geospatial Big Data initiative is. So when you start with this type of information, you can start to, instead of the show me there question of where you zoom in a particular location, you can then ask questions such as show me where, because we have, in addition to the satellite image, we have other layers of information that allow you to run analytics. So show me where all the remote dwellings are located. we're able to automatically extract this information from the imagery, which then creates vector data that's completely searchable, and we can run queries and analytics on that data. Another example, as I mentioned, show me where all the vehicles are located. So this is car counting. In this example, we're able to identify areas of new construction, so we're able to do automated change detection as well. And the key here too is that while some of these capabilities have been possible at the desktop level because of both the coverage of our archive as well as the cloud computing based algorithms where we can provision more storage and compute as necessary, we can actually run these algorithms at scale and do this on a global basis, which before wasn't possible. Now I'll turn things over to Sam.
Okay, so the solutions that Todd just mentioned were primarily automated. So we're running algorithms to extract data from images that were sourced by our constellation. But in many different cases, automation falls a little bit short. An algorithm can only extract a certain amount of data for certain features. There are some features that need to be identified by a human sitting at a computer and actually searching satellite images. The problem with that is resources. So to give you a real world example, we just completed a data set for the Indonesian government where our initial data pool was 1.7 million points of interest. We had 5 analysts working on this project, and within any sort of reasonable timeline, it is frankly impossible to search through all of that imagery and to search through each one of those data points to validate the accuracy. So we started thinking about this problem, and the solution that we came up with is, or at least the preliminary solution, is crowdsourcing. Now, crowdsourcing, just to give it a basic definition, is soliciting ideas, content from a group of people that are not traditional employees. So that's what you see here. So TomNod is where Digital Globe really started with crowdsourcing. Some of you may have heard of it. It's a platform that we use primarily for disaster recovery initiatives. TomNod, the system was created, I believe it was created in 2010 by researchers at UC San Diego. San Diego or San Diego State? UC San Diego?
I know it's San Diego.
It was San Diego. Either UC San Diego or San Diego State. And it was created initially in a search for actually the tomb of Genghis Khan. That was the original use for it. Digital Globe acquired the technology in 2010, and we started implementing it for, again, humanitarian purposes. So for example, when there was a hurricane, a tsunami, an earthquake, we would send the crowd of volunteers that had been built up to go actually tag points of interest and create data, extract data from within the satellite images that were sourced by our constellation. So that was the initial use. And the quote that you see here is directly from the TomNod website. It's open access. You're welcome to go visit it if you'd like. It's a team of online users who explore the Earth, solve real world problems, and view amazing images of our changing planet. So really what we're trying to appeal to when we're relying on this community of volunteers is what we call heartstrings. So these are heartstrings initiatives. It's opportunities to for people to feel like they're giving back.
And the search for MH370 as well as the Paul were two key events.
Right, so MH370, we had more than, so that's when the Malaysian airliner that went down, we had over 1 million volunteers log into our system and search swaths of ocean searching for debris. So this is another example. After the earthquake in Nepal, we had our community log in and map destruction. So the 3 tag types that you see are damaged buildings, major destruction, and damaged roads. Those are the 3 things that individuals were actually scrolling through imagery and looking for. So this is what the user interface looks like. Different tag types at the top left, and you actually, well, I guess top right for you. And individuals click and, well, no, top left. Individuals click and you can see who agrees, who disagrees. You can see different tags on the map. You can share images on Facebook. There's a forum where you can discuss. So a number of different functions. So this is a result. Yep.
Is consensus your quality control? Like,
okay, so I'm going to
agree on something. That's probably what it is.
Yeah, so I'm going to talk about consensus in a second. It's a great question, but that's I think might be the next slide. The next or the second next. So this is the results after the mapping initiative in Nepal. We had 61,000 taggers. Over 1 million tags placed and 5.8 million map views. And these are the results overlaid on top of a base map showing the different tag types that were identified. Okay, so like I said, we started crowdsourcing initiative in response to humanitarian crises. But what happens when we need to scale up data extraction in an area where there isn't some pull on the heartstrings? What if it's just an area that one of our customers is interested in? Let's say it's a rural area of Africa and we want to map settlements. The incentive for individuals to participate is now maybe not gone, maybe they still want to participate because they're interested in geospatial technologies, but the pull on your sense of altruism is no longer there. So what's the solution to this? So what we came up with is GeoHive. HIVE stands for Human Imagery Verification Effort. So it's essentially an open community of volunteers, exactly like TomNod, who create and validate geospatial data, but this time we offer incentives. So we had to replace the heartstrings pull with something else. What we replaced it with, to start, is money. So I'm going to talk about that. So how do GeoHive campaigns work? So you start with your customer request for information, or if it's just an internal search for something. The area of interest is enumerated, and the tag types that you're looking for are stipulated. Pre-production is we're downloading points of interest from public repositories for data. So OpenStreetMap, Wikimapia, GeoNames, GNDB, HotelSpace. And we're also downloading the imagery, the digital world imagery within that area of interest. We then call upon our crowd of users to actually go into the imagery and either identify points of interest as well as vote on the accuracy of the points that we've downloaded. The voting interface, so the interface that's used is exactly the same as the TomNod interface. It allows you to use hotkeys on your computer keyboard to assign values to the points that have been downloaded, and it allows you to use your computer mouse to click on the different features that you find. Now, getting into the incentives, we pay through a system called Amazon Mechanical Turk. I don't know if any of you are familiar. Mechanical Turk is a system owned by Amazon. It's essentially a hosting environment for computer-based tasks. Any company can create an Amazon Mechanical Turk account, upload work, and a crowd of volunteers, any individual with a computer and internet access, can log into the system and complete work for them for payment. So you have all sorts of types of companies in there. You could have, I've seen an example of Walmart having people itemize receipts. I've seen examples of DARPA having people translate documents. And in our case, it's individuals logging in and identifying points of interest and voting on the accuracy of points downloaded. So the amount of remuneration is between $8 and $11 an hour if you work at a consistent rate. For us, that's doable. Again, if we were paying full-time professional analysts to do this, we wouldn't be able to do it because you have to pay them full salary and benefits. Where in this case, it's individuals that maybe have some free time, they're interested in imagery analysis, and they want to make a little extra money on the side. So they go through the process, they analyze imagery, they tag points of interest, they validate other points, they receive payment, we receive the data back, and we go through a QA/QC process to actually make sure the data is correct. So what is this QA/QC process? And this will get into consensus a little bit. So there are three different processes that we go through to validate the accuracy of the data. The first is redundancy. So the terminology we use is coverage. So coverage refers to the amount of coverage you have, refers to the number of individuals who are required to look at an image before it is filed in our final geodatabase. So for example, if your coverage is 10x, X is the terminology we use, that means that at least 10 people have to look at an image tile and either tag points or vote on points before it is sequestered in your final database. So the point is, redundancy is a surrogate measure for accuracy. Second is agreement. So this is something called CrowdRank. It's a proprietary algorithm that essentially measures the extent to which an individual participant's contribution agrees with the contributions of all other participants. So to give you an example, you're looking at an image tile. There's a single point of interest in that image tile. And let's say we're having users vote on the accuracy of that point. They can either vote yes, as in, yes, that vector point is on top of the feature. No, it is not on top of the feature. 3 is needs adjustment. So we create a buffer zone around the point that's been created. And if the feature in the image itself falls within the buffer zone, but not within the internal circle, it needs adjustment. An analyst needs to go in and actually pick up that point and drop it on the actual feature. And then 4 is can't tell, which typically refers to blurred image or I can't see because of cloud cover. So that is So agreement is, again, so essentially each individual contributor is assigned a crowd rank score. Your crowd rank score fluctuates up and down over the course of a campaign, depending on how frequently you agree with other people. So if you find yourself in the majority agreement, crowd rank automatically assumes that you are correct, that the majority is correct, and bumps up the crowd rank score of all the individuals who agreed in that case. On the next image tile, the individuals whose crowd rank was bumped up now have more weight. Their vote is essentially counted as more valuable in crowd rank's determination of who is right and who is wrong. Conversely, the individuals who are not in the majority, crowd rank is bumped down, so their vote counts for less. So it's essentially a way of rewarding the individuals who are more accurate.
So one other comment on accuracy too is that there's, depending on how the capability is used, it doesn't necessarily go, even after all those algorithms, it doesn't necessarily go right into what the output might be. In some cases, so in the case of MH370, you actually had, it was really about narrowing the search. Right. So then you had imagery analysts go in and do more sophisticated analytics to then kind of take accuracy another step further.
Right, and I'm actually going to talk about that right now. So what Todd is referring to is what we call tip sheeting. So tip sheeting is essentially an inline QA/QC process. So as a campaign is ongoing, one of our analysts, it's been me sometimes, will actually sit at the computer and we can view a live stream of all the image tiles that individuals are looking at and voting on. So the Digital Globe analyst that does this is essentially treated as the super user. So when we validate whether or not the aggregate votes on a specific point of interest have been right or not, it automatically increases or decreases the individual's crowd rank scores that have participated, which in turn affects all other votes that those individuals have cast. So that is the inline QA/QC. Yes, sir.
So for the individuals that are not agreeing with the majority,
correct,
do they get shifted off of the project?
Okay, it's a great question. So I'll talk about that in 1 second. It's a great question.
What prevents people from scooping? There's money now involved.
Right, so this is a great question. Nope, it's a great question. So, so I'll answer it right now. So what you're really referring to is scammers. So when you have a system where you're willing to pay people, you can have someone that sits at a computer and just does this. And there is actually someone who built an algorithm which just cycled through image tiles. They said go, and it cycled, and we spent about $400. We paid that person about $400 before we caught them. So there are ways to catch those people. The first, but the most important, is our vetting process. So that's the third one, the third option you see there. So vetting refers to the creation and analysis of metrics after a campaign has been complete. Some of the metrics that we look at, for example, are features created over map tiles viewed. So if you're doing a discovery campaign where individuals are going into imagery and tagging points of interest, we can see, let's say one user viewed 100 map tiles and created 10 features. We can see another user who viewed 80% of the same map tiles and created 60 features. That is automatically a red flag to us that the first user was kind of just not really paying attention. They were just cycling through the imagery. To answer your question specifically, do we kick them out? The answer to that is no, because it is difficult to determine, to segment individuals who are deliberately submitting false data and individuals who are just frankly not good at it. Because there are some people that are less proficient in the discovery or analysis of points of interest in satellite imagery. So what we do is, as opposed to segmenting them and deleting them from our crowd, instead we promote the people who are good. So the people who are good are invited to campaigns that have a higher rate of pay, and the individuals that aren't as good are relegated to campaigns that are either lower priority or pay at a lower rate. So they're not completely deleted, but they're sort of put in a quote unquote lower group. The last thing is, for vetting, is we keep sort of ongoing records of not just who's good at this type of work, but who's good at this type of work for specific features. So one person may be really good at identifying electrical infrastructure. They can identify telecommunications towers, substations, transformers, power lines. They may be really bad at identifying baseball stadiums, let's just say. In our records, they are put in the upper group for electrical infrastructure and in the lower group for baseball stadiums. So when we run subsequent campaigns, we're now working with what we call a vetted crowd. The vetted crowd are the individuals who perform best for that feature type, which in turn improves the accuracy of our output. And it is a problem. I mean, it's been actually one of the major a major point of emphasis from my boss, who's constantly coming up to me and saying, so do we have any scammers? Do we have any scammers? Because we have a limited budget for this. So, I mean, the more money you give to people who are just submitting crap data, I mean, okay, so who are GeoHive participants? So when we first started, we started advertising on Amazon Mechanical Turk. So again, Mechanical Turk is the hosting environment for these sorts of tasks. Mechanical Turk includes forums where users can interact, communicate with each other, communicate with admins, and also our email address is hosted right in the Mechanical Turk forum. When we create a live campaign, every single person with a Mechanical Turk account can view that that campaign is live, and they can also view the rate of pay per each click. For the first campaign, we did an exceedingly high rate of pay because we wanted to attract interest. It resulted in my inbox completely exploding. I got about 200 emails in about 30 minutes from individuals who wanted to participate. They saw a very high rate of pay, and it ended up paying them about $15 an hour. So that was the initial basis of our crowd. We have individuals from Mechanical Turk who want to participate. After we built that initial basis, we started thinking about users who may not be so focused on money and are more interested in the experience of crowdsourcing and of geospatial technology. So logically, we thought about students, college and university students specifically. So what I started doing is sending cold emails to university professors. Jeff was one of the recipients of one of those emails. Actually, Wendy was, but it was forwarded to Jeff. And I reached out to, I started with the Centers for Academic Excellence of Geospatial Sciences, which is a designation given by NGA. There are 16 of them, and they're also USGIF accredited institutions. So I reached out to their geography departments and I said, hey, we're willing to pay students to do this type of work. If you have anyone that's interested, wants to make a little extra money, learn imagery analysis, learn how to recognize features, we would love for them to join. So that was the start. The last group is professionals. So we were reaching out to colleagues. There are some digital employees that do this in their spare time. People who are members of professional organizations like USGIF, those types of people. There's also retired military spouses, it really is anyone. So we ran into one more problem. We found that students were by and large not interested in the financial incentive. It was motivating to a very, very small extent, but what we were finding is that they were participating for a short amount of time and then they were logging off. It's hard to attract and maintain the attention of a student. They have classes, they have extracurriculars, they're busy. So we tried to think, what is a better incentive for this cohort? What can we provide them that motivates them to join our initiative? So we started from scratch. We created a brand new user interface that more closely simulates the experience of working in ArcGIS. It not only allows you to create points, but now you can create points, lines, and polygons, and you can also ascribe attribution. So it is closely related to OpenStreetMap, specifically the ID editor tool. And while I talk, I will show you it. So we call it the GeoHive editor. And this is what it looks like. This is our tasking manager. There's no audio, it's just, yeah. So essentially what you're seeing here is you're seeing an AOI. The AOI is divided into grid cells for individuals to work on. Individuals can be assigned individual grid cells, or they can just click a random task. So this person has gone into a random task and is now going to edit the features within that grid cell. Okay, so they're entering it right now. They're choosing a grid cell to work on. Now they're going to start mapping. So they're going to edit using OpenStreetMap's ID editor tool. It's exactly the same functionality, create points, lines, and polygons with a few key differences. Some of the differences are, first, the schema for attribution conforms to NGA's schema. It's not the OpenStreetMap schema, which is very extensive. The second is you can upload points from open sources into the map and have users validate those points. The third is users have access to DigitalGlow's imagery archive. So what you're seeing on the right-hand side is the user didn't like that image that they were looking at, so they chose a different image to overlay. And that carousel that you saw on the right is all of DigitalGlow's imagery, and it also includes metadata. So they can not only see the image itself, they can see when the image was taken, and they can see metrics about it, what the nadir angle was, what % cloud cover it has, and they toggle off the image depending on what looks best for analyzing it. So this user is now within the image itself, and they're digitizing a polygon. We call it an area in this case. Now they are adding attribution. There are a number of different fields they can fill out. And then they can edit the shape itself after it's complete, which I don't think they do in this case. No. Okay, so again, adding another polygon, create points, lines, and polygons, and add attribution. Depending on the campaign, we ask users to look for different things. Sometimes they're actually digitizing the landscape with shapes and areas and lines. Other times we're just asking them to drop points. But as you're seeing, this is a much more involved interface than TomNod. It allows you to do much more, and it's for someone who doesn't necessarily have the experience of feature creation. Another thing we discovered, and this really surprised me because I didn't start off as a geospatial person. I found out that a lot of, especially undergraduates, by the time they graduate, don't have experience in feature creation. What they have experience in is maybe looking at imagery, and a lot of times they're delivered canned data sets to manipulate or to analyze. But the process of digitizing, so creating points, lines, and polygons, and adding attribution is not something that they necessarily have in their wheelhouse. So this, again, is a professionally applicable skill that, for example, my colleagues use all the time. I mean, we have people that do this full time. So, as I said before, we created a system where we're offering, which offers both traditional and non-traditional incentives. By traditional incentives, we mean money. By non-traditional incentives, we mean the experience of working in a system that's adjacent to ArcGIS while not requiring you to work in Arc itself. Let's see what I have next. Okay, so the last thing I want to mention is another one of the major reasons that I'm here and sort of going around to different professors. So not only do we invite individual students to participate, what I've also started to do is reach out to professors in the interest of starting instituting capstone projects into their curriculum. So a capstone project is as follows. The professor requires their students to complete a certain amount of work within the GeoHive system, digitizing, which is dropping points, lines, and polygons, and adding attribution. The area of interest and the features themselves are agreed upon between the professor and Digital Globe before the project starts, as well as the project timeline. Students are not paid for the work, but at the end of the project, the professor is delivered a geodatabase for in-class use. So for all other users, they don't actually receive the data itself. In this case, we're actually delivering the file to the class for whatever purpose you see fit. It's not for public dissemination. It's something that has been discussed a little bit, and there may be some wiggle room on that. But again, my vision is something, I'll give you an example. So maybe students digitize the electrical infrastructure in Uganda. Over the course of 2 months, each person does one grid square every week. At the end of the project timeline, we deliver that GDB of crowdsourced results to the professor, and the students are then asked to write a development proposal on how best to develop that area of the world's IT infrastructure, or that IT footprint, using the infrastructure footprint, using the existing infrastructure, using the existing telecommunications towers, substations, transformers footprint. But again, that's just one example. The opportunities are sort of unlimited. So I'm going to hand it back to Todd. And also, I don't know if your interaction with undergraduates, but if you are interested in that sort of initiative, please come talk to me. Yep.
I'm taking a course.
Okay.
I'm thinking of the best way to get students in is if you could, well, my type of classes. So if you could package probably 1 week of lab work equivalent of digitizing, because throughout the semester, of course, you probably only have 1 week that's really for data creation,
yes.
Right? You have the other weeks, other topics.
Yep.
So for that data creation week, we could use a lab package,
yep.
Right? Every student, you got 30 students in the class or 50 students in the class, each one could go pick a package from what you can for them, an area, and then you have some assessment tools for that.
So the assessment tools is also something I should have mentioned. This is something that we generate. What we're willing to do is provide professors with analytics
Right.
during and following a campaign,
Mhm.
which shows number of grid cells locked, number of grid cells edited, number of features approved, a
Right.
whole
Right.
host of different things. And as far as project timelines,
Mhm.
we're flexible with that. So first of all, we're able to provide a menu of different options for professors to choose from, both in terms of the area that
Mhm.
students are looking in, as well as the types of features that they're being asked to create. So that really is a blank slate for us. I mean, I guess my point is, our real attempt is to create something that adds value, scholastic value for students, because if it doesn't do that, then why would any professor agree to this? So we want to be as flexible as possible, because there needs to be as good of an incentive for the professor as there is for us to do this. So in that regard, a week-long lab sounds great. I mean, there's really no time limit that we're married to.
Yeah, the key is to make it simple for the
Right.
start.
Yep.
Right? So that at the end, the professor probably isn't interested in getting the data, but the student might,
Right.
because a lot of the courses would have also a predetermined project at the end.
Right.
And the
Which is-
student could use the digitizing
Yep.
to actually prepare some data for her final project.
Which was that was our image. The other thing that we're starting to talk about is, so this is by no means approved by my boss yet, but we're starting to talk about delivering a free imagery scene, not free, but delivering an imagery scene for use in research and whatever you want, in exchange for a certain amount of digitization. Because the imagery itself is oftentimes what professors are interested in, because it helps with their research. I mean, access to high resolution imagery it's difficult. I mean, it's expensive. It's hard to get a hold of. So that's, especially for remote sensing people, that's really what holds value. And that's what something we're talking about. But exactly as you said, I mean, if the data is what holds value for students, then that's what we give them. So now I'm going to pass it back over to Todd. This is the last part of our presentation. In this part, he's going to sort of talk about, okay, so we've talked about capturing, so that's imagery and also capturing data from open sources. We've talked about extracting, which is extracting detailed information from those sources. And now we're going to talk about the analysis portion, which is what are we actually doing with all that insight?
Great, thanks, Ann. So if we had to characterize our analytic process just in a simple graphic, we think about different layers of data and information. So as Sam alluded to, that could be our satellite imagery as a base map. There could be data extracted from that imagery through both manual and automated or semi-automated means. There's other layers that we're able to create or we're able to aggregate from open sources or that we can create. Generally, with that stack of information, with a combination of both expertise, tradecraft around specific problem sets and domains, and a variety of analytic tools, some of which I'll touch on, we're able to then produce insight type of products, right? Which can be delivered either as a services-based engagement, can be delivered as a report. But basically, this is where we put all these things together and help to try to answer a key question for a decision maker. So what are the types of analysis that we do? This is really a variety of them, so let me touch on a few. In the upper corner, you can see a least cost path analysis. So how far can somebody travel over the course of, say, 4 hours? Where's the easiest path? You can see that. That's really a terrain-based analytics. So how much has the terrain changed? Where could I land a helicopter? Some of these analytics, more of the elevation and terrain-based analytics, are actually analytics that we're able to, I can talk more about that if you're interested in elevation data, but we recently announced a joint venture with Saab. The name of the joint venture is called Vricon, and essentially they have algorithms that they're able to utilize from our imagery archive by simply using coincident images to produce 3D models and digital surface models, which then these analytics can be calculated from. We also look at sources of data such as social media data in a location context. What are people talking about on social media in an open sense? What is the sentiment of that? And then when are there changes? So we can look for kind of anomalies, and that could either be a lot of people talking about a particular topic, or where you had a lot of people, kind of normal activity, a lot of activity, which then for whatever reason goes silent. And so we're able to look at those analytics at scale in the context of all of our other layers of data. And then In the lower corner here, there's an example, again, a more of a terrain-based analytic, where we're looking at radio frequency propagation, which actually takes into account, you can see the shadowing from buildings and so forth in an urban area, as well as then how far can I see from a point, so line of sight, or where would I be visible from a point. So this can apply across a variety of domains. You could even think about this in the context of commercial application, like advertising. If you place a billboard someplace, what people can see that billboard from which angles and where they're traveling along the route and so forth. So, sorry, go ahead to the sort of controlling our own slides. So those are all forms of analytics where we're able to essentially make an observation from data that's there. We also do more advanced analytics where we're able to anticipate or predict, and we fully recognize that the word predict can be a loaded term, and we're happy to discuss that further. But really, these are analytics, statistical-based analytics, where we're trying to anticipate risk and opportunities. Essentially, the way that we do that is we use that big stack of data that I depicted on the earlier graphic, and we look at a particular type of event or phenomena has occurred. So it has to be something that's observable. So we have the stack of data, those are our factors, and then we look at an event. And we analyze that event in the context of all of those factors of geospatial data, all those layers. And we look at where there's relationships between the events and the other data. So then we can, in a very data-driven, transparent way, be able to see which factors are most associated with those events, which make them suitable. And then that helps define what we call a signature for that type of activity, which then we can look to see if there's other places within a given area of interest that have a similar confluence of factors that would make an event of that nature suitable. Now, we can't say for sure that that event would happen. We can reduce a search area by upwards of 90%, so we can really say the areas that are most conducive to that. But obviously, these are it's a statistical-based analysis. That's an iterative cycle, and so this is something that we constantly are updating and training the models to better understand. This particular example, we were doing a risk-based analysis from some open source data, looking at attacks of Boko Haram, and we essentially were able to use this open information to look at where the attacks that had occurred and all the other factors that were in this geospatial environment. We then produced the orange areas, the yellow areas that you see. Those are the areas that were an output of a tool called Signature Analyst, which is our anticipatory analytics and modeling tool. So we're able to use that for these sort of pattern analysis. And then we're able to, so unlike traditional heat maps where it's simply showing a density of previous points or of a certain type of data that have occurred, this is actually doing this in an anticipatory way. And so the areas that you see here, this is anticipating events that could happen. And then what we did is we went and back tested the model. And if you see the text in the lower corner here, since 2012, so about 87% of the events that happened subsequently in the data that we back tested actually took place in areas that had been identified using this tool. The key benefit here with these sort of analytics is that we can help narrow the focus on areas that are at highest risk, or in the case, for example, of perhaps natural resource discovery or other types of opportunities, you can help focus in the areas where that type of resource could be discovered. And so with that, happy to take any questions. Appreciate your time and attention and all the questions that we received during the presentation.
Thank you very much. So we have this room till 1:30, so might as well take more questions, understanding that some people might have to leave now that it's 1 o'clock.
In terms of your crowd, this is just kind of a general curiosity question, but in terms of the crowdsourced analyzers you have looking at your imagery, do you focus on US only, or do you do worldwide?
So it's a great question. So Mechanical Turk